Hello everyone, I am Divya. I am from CSE Core. Today I am going to give you a presentation about application of finite automata in networking. Introduction to automata. Automata is nothing but a machine which accepts the string of a language L over an input alphabet alpha. There are four different types of automata. They are mostly used in the theory of computation. They are as follows: finite state automata, push-down automata, linear bounded automata, Turing machine. When comparing these four types of automata, finite state automatas are less powerful, whereas Turing machines are more powerful. Equivalence. Finite state machine is equivalent to the following: PDA with finite stack, Turing machine with finite tape, Turing machine with unidirectional tape, Turing machine with read-only tape. Push-down automata is equivalent to the following: finite automata with stack. Turing machine is equivalent to the following: PDA with additional stack, finite automata with two stacks. Applications of different automata. The applications of different automata in TOC are explained below. Finite automata. The applications of finite automata are as follows: design of the lexical analysis of a compiler, recognize the pattern by using regular expressions, use of the Millian-Moore machines for designing the combination of sequential circuits, helpful in text editors, and used for spell checkers. Push-down automata. The applications of push-down automata are as follows: used in the syntax analysis space, implementation of stack applications, used in evaluations of arithmetic expressions. Linear bounded automata. The applications of linear bounded automata are as follows: used in the genetic programming implementation, construction of syntactic phrase trees, Turing machine. The applications of Turing machine are as follows: used to solve the recursively enormous problem, used for knowing complexity theory, used for neural networks implementation, used in robotics applications, used in the implementation of artificial intelligence. Deterministic finite automata. DFA refers to deterministic finite automata. Deterministic refers to the uniqueness of the computation. The finite automata are deterministic FA if the machine reads an input string one symbol at a time. In DFA, there are only one path input from the current state to the next state. It does not accept the null move, that is, it cannot change the state without any input. It can contain multiple finite states. It is used in lexical analysis in compilers. Formal definition of different automata. A deterministic finite automata is a collection of defined as a phi tuple and is as follows. And whereas Q equals to finite set called states, and alpha equals to finite state called alphabets, and F equals to final or accept state. Q is the start or initial state. Graphical representation of DFA. A DFA can be represented by graphics called state diagrams. The following factors are considered in DFA. The state is represented by vertices. The arc labeled with an input character shows the transitions. The initial state is represented with an arrow. The final state is represented by a double circle. The applications of DFA. The different applications of deterministic finite automata are as follows: protocol analysis, text phrasing, video game character behavior, security analysis, CPU control units, natural language processing, speech recognition, etc. Applications of automata theory in networking. Automata are basic structure in computer science. Language equivalence, like example, well-studied several algorithm. Applications of finite automata in networking. Till now, we have discussed various fields in which automata theory is used, but now we are going to discuss in specific how automata theory is used in computing and networking. Network uses some protocols to transmit and receive data over the network, and the protocols that are used being below error control, flow control, bandwidth limitation, etc. Finite automata have several applications in networking, including protocol analysis. The finite automata can be used to analyze the network protocol to determine if they to a particular standard or specification. This is important in assuring interoperable between different network devices. The second one is firewall rules. Finite automata can be used to create firewall rules for network security. The rules can be based on patterns of network traffic and specify what traffic should be allowed or blocked. Instruction detection. Finite automata can be used for instruction detection by monitoring network traffic for patterns that indicate potential security threats. Traffic management. Finite automata can be used to manage network traffic by directing packets to specific destinations based on certain criteria such as type or destination address. The fifth one is routing protocols. Finite automata can be used in routing protocols to determine the best path for data to travel through a network. First one is protocol analysis. Finite automata can be used to analyze the network protocols to determine if they adhere to a particular standard or specification. A network protocol is a set of rules that governs communication between the devices on internet. Examples of network protocols include TCP, IP, HTTP, and FTP. To analyze a network protocol, a finite automata can be constructed that models the behavior of a protocol. This automation can then be used to verify that the protocol that conforms to a particular standard or specification. For example, let's consider the TCP protocol. TCP is a connection-oriented protocol that provides reliable, ordered delivery of data between applications running on different devices. A finite automata can be constructed that models the behavior of TCP, including the states and transitions that occur during the process of establishing and tearing down a TCP connection, as well as the mechanisms for assuring reliable delivery of data. Once the automation has been constructed, it can be used to verify that an implementation of TCP adheres to a standard specification. This can be done by comparing the behavior of the implementation with the behavior of automata under various scenarios and conditions. Any derivations from an expected behavior can indicate errors or non-conformance with the specification. In summary, finite automata provides a useful tool for modeling and analyzing network protocols that helps to assure that implementations conform to established standards and specifications. The next one is firewall rules. Firewalls are a critical component of network security infrastructure that protect networks from unauthorized access and attacks. A firewall can be thought of a gatekeeper that controls access to and from a network by enforcing a set of rules that determine which network traffic is allowed to pass through. Finite automata can be used to create firewall rules for network security. These rules can be based on the patterns of network traffic and specify what traffic should be allowed or blocked. A firewall rule typically consists of a set of conditions that must be met before a specific action is taken, such as allowing or blocking traffic. For example, let's say a company wants to block all incoming traffic from a particular IP address. A finite automata can be constructed that models the behavior of its rule. The finite automata would have a state that represents the initial condition where no traffic has been received from a specified IP address, and a state that represents the final condition where all traffic from the specified IP address has been blocked. The transitions between these states will be determined by the pattern of traffic received from the IP address. Once the automata has been constructed, it can be used to implement the firewall rule by configuring the firewall to monitor incoming traffic and apply the rule when the specified conditions are met. Overall, finite automata provide a useful tool for modeling and implementing firewall rules, and which improve the network security by controlling access to network resources. Next one is instruction detection. Detection is a critical component of network security that involves monitoring network traffic for patterns that indicate potential security threats. Instruction detection system can be used to detect a wide range of security threats, including malware, unauthorized access attempts, and denial of service attacks. Finite automata can be used for instruction detection by monitoring network traffic for patterns that match known attack signatures. An attack signature is a unique pattern of network traffic that is associated with a particular type of attack. For example, a signature might be associated with an SQL injection attack or a buffer overflow attack. To detect these signatures, a finite automata can be constructed that models the behavior of the attack. The automata would have states that represent the different phases of the attack. Example, initial exploitation and exfiltration, and transitions that correspond to specific network activities. Example, sending a particular type of packet or making a specific request. Once the automata has been constructed, it can be used to detect attacks by monitoring network traffic and comparing it to an expected behavior of the automata. If the traffic matches the behavior of the automata, an alert can be generated indicating that a potential attack is underway. Overall, finite automata provides a useful tool for instruction detection and can help to improve network security by identifying potential threats in real time. The other one is traffic management. Finite automata can be used to manage network traffic by directing packets to specific destinations based on certain criteria, such as protocol type or destination address. This process is known as traffic management or packet filtering. To implement traffic management, a finite automata can be constructed that models the behavior of the network traffic. The automata would have states that represent different states of the network communication and transitions that correspond to specific actions, such as forwarding packets to a particular destination or dropping them. Once the automata has been constructed, it can be used to manage network traffic by configuring routers or switches to use the automata to filter incoming packets. For example, a router might be configured to forward packets that match a particular pattern to a specific destination, while dropping all other packets. Traffic management can be used to optimize network performance by ensuring that packets are directed to their intended destinations efficiently, and to control network traffic by prioritizing and or limiting traffic based on specific criteria. Overall, finite automata provide a powerful tool for traffic management in networking and can help to improve network performance, reliability, and security. The other one is routing protocols. Finite automata can be used to analyze network traffic patterns to detect anomalies and diagnose network performance issues. Anomaly detection is a process of identifying unusual patterns of network activity that may indicate a security breach, while performance analysis is a process of identifying network bottlenecks or other issues that are causing slow or unreliable network performance. To analyze network traffic, a finite automata can be constructed that models the behavior of normal network traffic. The automata would have states that network of different stages of communication and transitions that correspond to specific actions such as sending packets or establishing connections. For example, an anomaly detection system might use a finite automata to model the behavior of normal traffic and compare it to the behavior of incoming traffic in real time. If the incoming traffic does not match the expected behavior, an alert can be generated indicating a potential security breach. Initiate automata provide a useful tool for analyzing network traffic and identifying anomalies and performing issues. By detecting and addressing these issues, network performance and security can be improved. Conclusion. In conclusion, finite automata are powerful mathematical models that can be applied to a variety of problems in networking, including protocol design, instruction detection, traffic management, and network analysis. By using finite automata, network engineers and security professionals can better understand and optimize network behavior and detect potential security threats and diagnose and resolve performance issues. The versatility and flexibility of finite automata make them an essential tool in modern networking and security applications, and their continued development and application will undoubtedly lead to further advancement in these fields. Thank you.